Hello and welcome to Interactive Biology TV, where we're making biology fun. My name is Leslie Samuel. This is episode 13, where we're going to be talking about the action potential. I'm basically going to be giving you a review of the concepts that we've been talking about up to this point when it comes to the action potential. Over here, we have our neuron. And the part of the neuron that we are going to be focusing on is the axon. So that's this region here, starts here, and it goes to about there. Now what I'm going to do is I'm going to take a section of the neuron. So let's say I'm going to take this part here, and I am going to draw it down here. So here we have the axon. This is inside the axon, and this is outside the axon. Now, if you remember from a previous episode, outside the axon, we have a lot of sodium ions. So I'm going to draw sodium ions here, and they are all outside the cell. Now let's look over here. Here we have a stimulus that's happening, and you can see there's a first stimulus that does not reach threshold, so nothing happens. Another stimulus comes, it does not reach threshold, so we still do not get an action potential. If we have a stimulus that's strong enough, and I'm going to draw another stimulus in here. So let's say we have a stimulus that's that big. That's going to reach the threshold and cause an action potential. When that happens, voltage-gated sodium channels are going to open, and that's going to cause sodium to rush into the cell. Of course, that's going to start at the axon hillock. Sodium is going to rush in, making the membrane potential even more positive, causing more channels to open, more sodium to rush in, more sodium to rush in along the axon. What is that going to do to the membrane potential? You can see right here, this is where we get depolarization. The membrane potential goes up and up and up and up, and it's trying to reach the Donan equilibrium for sodium ions. And that equilibrium potential is somewhere around 58 millivolts. So sodium is rushing in because of the driving force causing sodium to go in. Sodium wants the membrane potential to go up to its Donan equilibrium, and that is around 58 millivolts. At this point, voltage-gated potassium channels have enough voltage in order for them to open. So I'm going to erase all of this now, and we're going to take a look at the axon again. I'm going to draw it here in blue. And inside the cell, we have a bunch of potassium ions. Now we have such a positive charge on the inside that potassium ions want to leave because positive repels positive. When voltage-gated potassium channels open, potassium can now leave the cell. So we have a lot of positive leaving the cell. And what that is going to do is cause repolarization, where the membrane potential is going down. Just like with sodium, potassium wants to reach its equilibrium potential, which is somewhere around negative 93 millivolts. And that is why the membrane potential is going down as it's leaving, because potassium wants the membrane potential to be at negative 93 millivolts. That is where it is most comfortable. Considering that the resting membrane potential is around negative 70, the membrane potential goes significantly lower than that negative 70, and this phase we call hyperpolarization. All along this process, we have the sodium-potassium pumps that are pumping sodium out of the cell, 3 sodium ions out, and 2 potassium ions back in. and that's going to cause the membrane potential to eventually reach back to its resting state. This is the entire action potential, looking at depolarization, repolarization, hyperpolarization, and it getting back to the resting state. I hope that makes sense. If you have any questions, feel free to leave them in the comments below. I'd be happy to answer your questions and maybe even make a video answering your specific question. That's it for this video, and I'll see you in the next one.